So this brings us to the last speaker of this session. It's Joan Tarrús from sedak, and he shall talk about game changer in architecture, multicurved tempered glass.
Good afternoon, everybody, and thank you for your interest and in this session. Thomas Hedewig, in his book Human Eyes, he tells us that the architecture of the last 100 years, it's boring. Back in 1989, he was at design school, still studying design, and he bumped into a book about Gaudi's Casa Milà in Barcelona. And he says that that actually opened a crack in that fixed reality of his, where all the old buildings were fascinating, while the modern buildings were almost always dull and boring. So here we have Casa Milà in Barcelona. He describes the building as so three-dimensional. So the opposite to all those flat, two-dimensional modern buildings. But despite being a modern building, and not an ancient castle or a royal palace from distant era, he says it proves that we can design modern buildings that look so as beautiful and appealing as a work of art. So he says buildings in the last 100 years are too monotonous, too flat. They would all fit more or less in rectangular shapes. They are too serious, look like they've been designed for serious people. Lack of personality, lack of details at windows and doors and entrances and roofs. So what's so scary about the curve? He considers boring as inhuman, as antisocial, inhuman. So he thinks we have to design buildings that are better for us to live in, to work, to learn, to heal. So we need to rehumanize. So in the end, we all feel better in nature. Animals do not live in boring spaces at all. So let's take a look. I mean, animals create and live in very sophisticated homes. For instance, spiders on this sophisticated combination of curves and lines. So humans feel attracted by buildings that have complexity, but also a proper combination and balance between complexity and repetition. And actually, Casa Milà, back to Gaudi's in Barcelona, is a very good example of that, of complex facade, complex geometries in the balconies, but also a right balance of repetition. In glass, what a better example than Elbphilharmonie in Hamburg by Herzog and de Meuron. Very complicated facade and glass geometries. And actually the right balance of complexity and repetition. The curved double glazed units of this building were produced in our facilities in Sanglas in Italy. And I like to share some of these beautiful pictures in the presentations where, I mean, pictures that convey really so well what's behind this business, what's behind the complexity, the artisanship of glass bending. No? So overall, when we think about slumping glass, what we also call gravity bending, a technique that we would use to manufacture glass, complex geometries, as the ones we have at the Elbphilharmonie. So we always have to think about manufacturing bespoke molds to very high precision. And basically, well, slumping the glass is a process that has many pros and cons. We can do any shapes. We decide the shapes. We make bespoke molds to very high precision. Glass resulting from bending has a very good optical quality. It's good afterwards to run precise lamination, but it has also some disadvantages, clearly. Which, I mean, generally the glass is generally weak for the most of the structural applications. So it's good because we can provide exceptional geometries, but glass is generally too weak. Worth to mention projects like, a little bit different, I mean, not building, but high quality glass, curved glass cabins for the ferry wheel in Dubai or the London Eye, both projects produced in our facilities as well. In all these cases, we have to think about, we are stuck to the traditional bending processes. So making a mold to precision and bending the glass with exceptional optical quality. There's no other way. But let's take a look to the process. I mean, throughout the years, I mean, we've been delivering exceptional geometries to very unique, outstanding buildings and facades by using this process. So heating up the glass, one light or more, one over the other, over the mold, at around 600-700 degrees, transition temperature, the glass slumping slowly, 8 hours process, long process, expensive. We need to make a mold for every single different shape. Afterwards, once the glass is curved, we can proceed with double glazing, lamination, double glazing, triple glazing. But structures like these, like at Penn Station in New York, beautiful. Yeah, the glass is feasible, the geometry is feasible, we can slump it, but the glass is not strong enough to withstand the loads or the tensions created by the metallic fittings and this flexible structure. So, luckily, we have technical solutions for that. So once the glass is slumped, we can take light by light, individual lights, and submit each glass light to a chemical process, what we call chemical toughening, chemical strengthening. So we have solutions to strengthen the glass afterwards. Expensive, yes, but effective technically. Process, probably you know, basically consists in putting the glass, any sort of geometry, from a flat piece of glass to a very complicated geometry that we have previously slumped over a mold. We put that in a bath at 460 degrees approximately centigrades for 24 hours. I mean, the time depends on what we want to do. And there's an ion exchange of smaller sodium ions on the glass surface, exchanged by bigger potassium ions. So with this technique, we can easily reach around 380 megapascals of surface compression with soda lime glass. A good example of the use of this technique is these circular skylights that we recently delivered to the Museum of London, where the glass is slumped first. The inner set here on the left stays annealed laminated, so gravity bending, annealed laminated with a high-performing Lowy coating on the convex surface facing the argon cavity. But the outer layer is submitted to chemical strengthening so that we can have a glass that is strong enough to withstand any sort of external loads, thermal loads, mechanical loads, any of them. Logically, one of the big disadvantages of chemical strengthening is that we cannot have anything on the surface. We cannot have a ceramic fluid. We cannot have a Lowy or solar control coating. Nothing. So in this case, at the outer layer, we are sandwiching the solar control interlayer, and we are sandwiching a printed interlayer with a dot pattern. When we think about glass for building in general, it's this. In general, it's what we call machine bending, thermal bending. So bending, toughening, bending, and heat strengthening. The process is known. It's a very fast process. Glass gets onto the rollers, keeps moving to avoid roller wave distortions, reaches the right transition temperature, moves to a second section. Glass is bent in 5 seconds, super fast, very fast production. And afterwards, basically, we cool down the glass. We quench the glass symmetrically so that the glass is properly toughened. Afterwards, logically, we can proceed with any of the configurations, laminating the glass and double glazing. But glass like this is always produced in equipment like this, actually. Equipment where the rollers of the oven basically can be lifted by the sides, lift it up, generating cylindrical, simple geometries. So it's a process that is excellent because it's inexpensive, it's fast, makes the glass strong, but it's limited in geometry. So the central axis at the bottom of the oven is totally fixed. So we can just generate certain range of radii, but that's all. We are limited to cylindrical geometries. And the glass always oscillates in the long direction. Projects like Giardini in northern Italy that have been recently delivered have been produced with this oven. The panels span around close to 9 meters, 8.6 meters, the largest, double-glazed, high-performing coatings. But with this same oven where we have produced these units, these double-glazed units, we can produce even more than double this size, so close to 18 meters. But again, limited with geometry. Sometimes we come across projects like these from architects, designers that are pushing the envelope, raising the bar again, so asking for things that we cannot produce, at least with the existing equipment. In this case, Zaha Hadid's tower in Hong Kong, the bottom part of the building has this 4.5 meter arc length running vertically, toughened, laminated with high reflectivity coatings, doubly curved, panels that theoretically were not feasible. At that moment, we decided to invest in a more sophisticated equipment. In this case, equipment that would be able to be lifted by the four corners. Lifting up again. So being able to bend in two directions, really. Being able to manufacture and deliver spherical panels. But having an oscillation of the panel in the long direction, so also once again being very limited, and also because the center of this rolling structure is fixed to the main structure, so this oven cannot go up and down, just the four corners, so not being able to do any sort of anti-clastic geometries. That's a view inside out of the same building. I think it's good to show that because it's the first time glass like this has been produced, and so spherically, doubly curved, toughened, laminated, and the optical quality is outstanding. During the last editions of Munich Bau in Germany and Glastic in Düsseldorf, we already went one step ahead, producing this very complicated unit by setting up or by preparing a customized setting up within that oven. So putting everything upside down and doing something very, very special to see the options of that equipment. And we realized it was feasible, but the next step was already very clear. How we can do that with an totally automatized setting up. Otherwise, to manufacture panels like that with totally bespoke configurations would take hours or days to make one single panel. So back to Gaudi in Barcelona and his buildings and his designs, he used to use hyperbolic paraboloid geometries in his designs because of the structural behavior of the structure, of the design, of the geometry, but also because of the beauty of it. So this is a geometry that we consider the most complicated when we are bending glass because we are bending in two directions. While when we have synclastic geometries, like a little bit like a sphere, we are bending and stretching in one direction. But when we have an anticlastic geometry like that, we are doing that in two directions. So there's a risk of generating wrinkles, and it's a very complicated geometry. It's the most complicated geometry we can face. But we are so thrilled to announce here at GPD. I mean, we had a totally different presentation to talk about anisotropies in flat and curved glass. So anisotropy-free glass, actually. But we decided to change it at the very last moment to come with this presentation because we are actually taking advantage to announce that we have designed and manufactured in-house a new equipment that is able to do very complicated geometries, double curvatures, anticlastic geometries actually, toughened or heat strengthened, so machine bent. So it's the next evolution and definitive evolution of all the ovens we've seen in this presentation. This new equipment is able to make a bit bigger than Jumbo, than the European Jumbo, so 8.5 by 3.6, but also deeper. I mean, the ovens we've seen in the presentation, machine bending, are normally able to produce up to 700 millimeters of depth. So within that, we can do different radii and different angles of curvature. But in this case, we are going to double that. So that is already telling us that we can do really crazy geometries in this oven. What's very particular about this design and this new equipment and this technology that we have developed in-house is that the oven transforms flat glass plates into any sort of complicated geometries within certain limits, of course. And the glass travels from the very beginning, where the glass is curved at the transition temperature, is traveling totally supported till the end, till it gets to the quenching area for toughening. So this specific fact makes super complicated geometries feasible, even geometries that would not be feasible with a slumping business. The process logically does not take 8 hours or 10 hours like in the gravity bending, traditional bending. It takes the same time it takes to make a cylindrical toughened glass, so between 15 and 20 minutes. About coatings and ceramic frites, before anybody asks, also feasible. So any sort of coatings that are available for flat, toughened glass, we can also use. We can also curved as well as ceramic frites. With this new oven, if we go back actually, we can see that as we can generate any sort of geometries, concave, convex, and twisting, I mean, we don't have to worry any longer where we have the coating, whether it's on the convex or the concave surface. We don't care. We have the coating always on the air side, logically, on flat surface, coatings or ceramic frites, and the glass afterwards, logically, is curved and toughened. With equipment like that, logically, we would not be able to operate if we hadn't logically developed software. So we have developed also in-house bespoke software for us to be able to analyze beforehand, even at design stage with the designers, whether or not those geometries that the architects are designing are feasible. So we have bespoke software that we put at your service. You can send us geometries for future projects, for existing projects. We can analyze and confirm that the geometries are feasible. So why not wondering whether or not today we would be able to manufacture this facade, these complicated, super complicated glass geometries, either heat strengthened or toughened. And we checked, and it's feasible. So we are absolutely ready for new emotions, to generate emotions, and to give answer to new designs from architects. So we hope that you are also ready for new emotions. So a real game changer. Thank you.